Let's be honest. In the world of large language models, we're obsessed with accuracy. We chase higher F1 scores, we benchmark against SCAD and GLUE, and we celebrate every percentage point. But here's the hard truth. Accuracy is a terrible proxy for reliability. A model can score 85% on a test set and still completely fall apart when you change a single synonym, or when you introduce even a tiny bit of internal noise. Today, we're diving into a rigorous study that actually measures what matters for production systems: the reliability of BERT-based question-answering models under controlled perturbations. We're looking at 4 heavy hitters in the transformer space: the original BERT base, RoBERTa, DistilBERT, and LLBERT. These encoder-only architectures have redefined extractive question answering. But when we deploy them in real-world applications, we don't just need them to be right once. We need them to be consistently right, even when the input phrasing shifts or when internal stochasticity kicks in. This research tackles that exact gap. They evaluate reliability through 2 distinct lenses: internal model variations using Monte Carlo Dropout and external input variations using controlled paraphrasing. First, let's talk data. They didn't just run everything on one benchmark. They used SCAD2 and KC. SCAD is fact-based, with independent questions that generally play to the strengths of BERT variants. KC is conversational and context-dependent, forcing the model to track dialogue history and resolve coreferences. This dual dataset approach is crucial, because it lets us see if a model's reliability is tied to its raw accuracy, or if stability is a separate architectural property. For internal stability, they activated Monte Carlo Dropout during the inference phase. For those unfamiliar, dropout is a regularization technique where you randomly zero out neurons during training to prevent overfitting. Monte Carlo Dropout flips that: you keep it active during testing. This forces the network to sample from its posterior distribution, giving you multiple stochastic predictions for the exact same input. But here's the technical catch: you can't just throw random dropout rates at it. They systematically swept rates from 0 to 35%. The data showed that anything below 5% didn't induce meaningful variance, while rates above 15% caused severe information loss, with models starting to output blank responses. The sweet spot? 10%. At 10%, you get a statistically significant widening of the performance distribution without breaking semantic alignment. This empirically justifies using MCD as a reliable uncertainty quantification framework. For input stability, they used a pre-trained BART-based paraphrasing model. But they didn't just feed random rewrites into the QA models. They implemented a strict semantic filtering pipeline. They computed cosine similarity between the original and paraphrased questions using Sentence-BERT embeddings, and only kept paraphrases falling between 0.75 and 0.98. Why that range? Below 0.75, the paraphrase drifts too far semantically, testing comprehension rather than lexical sensitivity. Above 0.98, you're just getting near duplicates with trivial lexical swaps. This interval isolates the model's true sensitivity to surface-level phrasing while preserving the underlying meaning. How do they measure it? 2 primary metrics. Cosine similarity evaluates semantic alignment between the predicted answer and the ground truth in the dense embedding space. It's scale invariant, so it catches when a model says the right thing in different words. Then there's the F1 score, the harmonic mean of precision and recall, which measures exact token overlap. They track the mean and standard deviation of both metrics across hundreds of stochastic samples. Low standard deviation means high reliability. Let's look at the MCD results. On SCAD, DistilBERT actually showed the tightest semantic coherence for answerable questions, with a cosine similarity of 0.899 and a notably low standard deviation. RoBERTa dominated the unanswerable category, showing remarkable stability when handling null responses. The most important finding here: enabling dropout during inference does not disrupt the model's learned representations. When they computed the correlation between unperturbed and perturbed outputs, RoBERTa hit 0.86 on SCAD and 0.87 on KC. BERT base and DistilBERT exceeded 0.9. This high correlation proves that MCD is a non-disruptive, valid method for measuring internal uncertainty. It doesn't break the model, it just reveals its confidence boundaries. They didn't stop at averages. They ran Welch's t-tests comparing RoBERTa and DistilBERT. On SCAD, the p-value was effectively 0, confirming a statistically significant performance difference under stochastic variation. On KC, the p-value was 0.45, meaning the models performed indistinguishably. This is a critical insight. Model reliability is highly context-dependent. You can't assume a model's stability transfers across different QA paradigms. Now the paraphrasing results. This is where lexical reliance really shows. On SCAD, RoBERTa maintained the highest semantic alignment and F1 scores across both answerable and unanswerable categories. On KC, LLBERT actually pulled ahead slightly in semantic consistency, though RoBERTa remained highly competitive. BERT base and DistilBERT fell behind when faced with paraphrased inputs. They ran pairwise Wilcoxon-Sindrank tests with Bonferroni correction to account for multiple comparisons, and the results show that most model pairs are statistically distinguishable. The takeaway: RoBERTa and Albert are the most robust to input phrasing variations. But even they struggle when the lexical structure shifts enough to trigger surface-level matching, rather than deep semantic reasoning. Architecturally, this makes sense. RoBERTa's dynamic masking and extensive training corpus force it to learn more robust contextual representations, while Albert's factorized embeddings and parameter sharing, though efficient, can introduce higher variance under perturbation. And here's where it gets interesting. They pulled a stratified 10% sample and had human annotators review predictions that automatic metrics marked as incorrect. They used FLES kappa to measure interannotator agreement, which came out to 0.78, indicating substantial agreement. What did the humans find? Nearly half of the incorrect predictions were actually semantically valid. RoBERTa's human-verified correct rate jumped to 45.79%, compared to 39.25% for DistilBERT. This proves that strict exact match metrics severely underestimate semantic validity. Models are often right, just not in the exact words the dataset expects. Let's look at failure modes. Under MCD, you see models outputting blank responses or outright hallucinations when the dropout rate pushes internal representations past a stability threshold. Under paraphrasing, you see lexical traps. Ask a model about Newton's second law, and it might confidently output inverse proportionality when the question actually asks for the law's name. This reveals a structural weakness. Even high-accuracy transformer models still heavily weight surface-level phrasing. They haven't fully decoupled syntax from semantics. You might be wondering, what about large language models? The authors actually ran a control experiment with TinyLlama. The results were brutal. Average cosine similarity, and F1 scores stayed below 0.5 across both datasets. Why? Because generative LLMs are optimized for open-ended text synthesis, not extractive QA. They're not designed to pinpoint exact spans in a context window. This reinforces a crucial point. For structured, reliable question answering, encoder-only models like RoBERTa and DistilBERT are still the architecturally superior choice. So what's the bottom line? Accuracy and reliability are fundamentally decoupled. You can have a model that scores 80% on a benchmark, but exhibits wild variance under minor perturbations, or a model that scores lower but remains rock solid. If you're building production systems, you need to evaluate both. RoBERTa emerges as the most consistently reliable architecture across both internal stochasticity and input variations. DistilBERT excels under internal MCD perturbations, making it ideal for latency-constrained environments where uncertainty quantification is critical. And Monte Carlo Dropout, when calibrated to around 10%, is a highly effective, non-disruptive tool for measuring prediction stability. This research shifts the conversation from how accurate is your model to how trustworthy is your model. In an era where AI is being deployed in healthcare, legal, and customer-facing applications, that distinction isn't just academic, it's operational. If you want to dig into the full methodology, the statistical tests, or the code repository for this framework, I've left links in the description. Thanks for watching. Keep questioning the benchmarks, and I'll see you in the next one.